Okay, so this is a question from chapter heat transfer. Okay, the question is three very large plates of same area are kept parallel and close to each other. They are considered as ideal black surfaces and have very high thermal conductivity. The first and third plates are maintained at temperature 2T and 3T. What is the temperature of the middle plate? So these are the plates, okay, which those have certain areas, same areas, right? This temperature, this plate has a temperature 3T, this plate has temperature 2T. We need to find the temperature of this middle plate, right? So they have an area, so they will be somewhat like this, right? So both the plates are releasing radiations, right? Like this one, right? So what I'll do here, we'll calculate the rate of heat, okay, absorbed by the middle plate. So the middle plate is absorbing heat, okay, from both the plates, okay, whatever is absorbed, okay. So we are assuming that there is no energy loss. So we'll see here. So let's say this right side plate is releasing the radiation, okay, at a rate of P1, and this one is releasing at a rate of P2. So the rate of radiation which is absorbed by the middle plate will be P1 plus P2, right? So this much heat was absorbed in form of radiations, right? So what is P1 here? So P1 is sigma, both are ideal black surfaces, so the emissivity is 1. So sigma A 3T to power 4 plus P2 is sigma A 2T to power, sorry, my mistake, just 1 second. Yeah, okay, so yeah, it's correct here. So sigma is 3T to power 4 plus sigma is 2T to power 4. So that is the total radiation which was absorbed by the middle plate. So we'll solve this one. So it will come as 81 T to power 4 plus 16 T to power 4. So it will come as sigma A 97 T to power 4. Okay, so that is the heat, the radiations which was absorbed by the middle plate. Now we need to find the temperature. So what we can say, suppose the temperature of this one is T naught. Okay, this is also an ideal black surface. This also has the same area. So what we can write P as sigma, okay, the absorbed one, sigma, okay. As you can see that the middle plate is absorbing heat, okay, from both the sides, right? So this side will absorb heat, the other side will absorb heat. So ultimately the surface area will be considered as 2A, okay, A and A. So sigma 2A T naught to power 4 is equal to sigma A 97 T to power 4. So here sigma cancelled, so we'll get T naught is equal to 97 by 2 into T to power 1 by 4. Okay, so that is the answer of this question. So let's move to the next question. There's one more question on this same topic, heat transfer. So let's see. So this question is two conductors A and B, each of cross-section areas 5 centimeter square, connected in series with this variation. Okay, the variation is in form of temperature and the distance. Thermal conductivities are 120 and 40 K. So we need to find the value of K here, this one. So it is again a straightforward question. What we'll do here, the two rods are there, 2A and B, they are in series, right? Okay, and what we can do, we need to find the temperatures at the end point. So this one is 0 degrees Celsius from the graph, and if we calculate this length here, so the angle is tan 53, which is 4 by 3. So 4 by 3 is equal to, let's take it as y upon 25. So it is coming as 100 by 3, and again this will be this is 45 degrees, so it is 50, so it is again 50. So that means the temperature is 100 by 3 plus 50 plus 50. So it can be written as 150 by 3, so 250 by 3. So that means the temperature at this end is 250 by 3. So now we know the temperature difference. So now we can calculate the current here. So current is equal to the temperature difference, which is 250 by 3 minus 0 upon the total resistance. So that is the current, and which will be same here. We need to find the temperature at this point, right? So we can compare it with the resistor here. So current is gonna be same. So now we need to find the resistance of A. So what is the resistance of A? So formula is L by Ka. So L is 25 centimeter upon K is 120 into A. A is 5 centimeter square. And what is RB is length is 50 centimeter upon it is 40K into 5 centimeters. So the resistance R is the sum of these two, right? RA plus RB. So let's write the temperature difference across A. So the current is flowing in this direction, right? So we can write T minus 0 is equal to IR, right? The current is 250 by 3 upon R. What is R here? This one. So we can do one thing. We can take the something common. Okay, so 25 centimeter by 40 into 5 centimeter square. So I'm taking something common, right? So 25 centimeter by 40 into 5 centimeter is common. So on the left hand side we'll have 1 by 3 plus on the right hand side we'll have 2 by K. Okay, so I took common and into R. So that is T minus 0 equal to I into R. What is R? RA, which is 25 centimeter upon 120 into 5 centimeter. So see, this are cancelled here. It is 3 is cancelled. Okay, so it's calculation part. Okay, so now what is left here? So we'll have 250 by 3 multiply 9 into then here we have K plus 6 upon 3K. So I took calcium here, and that is equal to T minus 0. Okay, we need to find the value of K, so we need to put the value of T from the graph. So T we know it is 100 by 3, right? So it is equal to 100 by 3. So it is cancel 5 5s are 25. Okay, again cancel 3 maybe cancel ho gaya. So what is left now? So 5 K, okay, is equal to 2K plus 12. So it is 3K is equal to 12. The K value is coming as 4, and that is the answer of this question. So I hope you understood, right? Okay, let's move to the next question. I selected one more question, and again it is related to the radiation now this time. Same topic, heat transfer. Okay, so this question is could be confusing at first sight, but when we'll try to solve, so it is very straightforward question. See, the average spectral emissive power, that means it is spectral emissive power is E lambda, right? So average, so how do we write average? So E lambda d lambda, okay, over the wavelength divided by d lambda. So this is the average spectral emissive power, okay, over the wavelength. That is given as 1 watt per meter square angstrom. Now integration d lambda is the change in wavelength, which is given like 0.2 to 1.2. So difference is 1 only, 1 angstrom. So from here like we will get E lambda d lambda is equal to 1 watt per meter square angstrom into 1 angstrom. So 1 and 1 is cancelled. So we have 1 watt per meter square. Now the thing is like if we see the unit, so you can see easily that it is a intensity unit, and we need to find the average power. So how can we get the power from intensity? So just by multiplying the intensity with the area. We know that intensity is equal to power by area, power per unit area. That's how we define. So what is the power then? Intensity into area. And like from the value unit also, like we can say how to get watt from watt per meter square. So we just need to multiply with the surface area. So that's it. So if we multiply this thing with the surface area, which is 5 meters square, so see, if you see the unit, you will get power, and that is 5 watt, and that is the answer, right? So that's straightforward it is. Okay, so I hope you understood this thing, average power, which is intensity multiplied by area. Clear? Okay, because this is intensity only, right? If you multiply this with the wavelength, so it integration E lambda d lambda, so that E only, that like the emissive power, we call this E as a emissive power, which is like radiation per unit area. That is nothing but the intensity. You getting my point? So that's why like I just multiply this with the area, so to get the watt power, which is radiation per unit time. Okay, so that's it. Okay, let's move to the next question now. Next question, okay, this one is related to the current electricity. Okay, it is not related to the heat transfer, but this question is very good question. That's why I took this one here. So let's see this question. What is it? Okay, in this question, a cell of internal resistance 8 ohm supplies same power to load resistance for two different values of load, R1 and R2. We can choose only integer value of load resistance, then maximum value of R1 plus R2 we need to find. So there are two circuits. This is one load connected with a cell with internal resistance R, and this is another circuit connected with the same batteries with internal resistance R2. It says that that cell provides same power to the two loads, okay, R1 and R2. So what is the power supplied here? So we have power across the R1 here. So I square R, that is the formula I am going to use, I square R. So power P1 is equal to I square. What is I here? So E square upon R plus R square into R1. And what is P2 here? E square upon R plus R. Sorry, it is R1 and R2. R2. And they are equal. So we'll equate them. And from here we'll start our calculation part. So R1 plus R whole square, R1 equal to E square upon R2 plus R whole square R2. So this cancel here. Okay, now we'll separate. So R1 by R2 is equal to R1 plus R upon R2 plus R whole square. We'll take a square root here. So R1 root R2 is equal to, and I'm taking R1 R2 common. Okay, so it is 1 plus R by R1, 1 plus R by R2. So we can see like it's cancel here, root will come here. Now cross multiply, just send this term to the left hand side. So root R2 root R1 is equal to 1 plus R by R1 upon 1 plus R by R2. Now cross multiply. So cross multiply root R2 plus R by root R2 is equal to R root R1 plus R by root R1. Now separate the similar terms. So root R2 minus root R1 is equal to R 1 by R1 minus 1 by root R2. Now one more step we'll write. Okay, now see, this is cancelled. So what we have here now, so root r1 r2 is equal to r. So if we see the r1 r2 equal to r square, and r value is given 8, so that is 64. Up see now that registers r1 r2, the product is 64. Up they are asking like the choose only integer value, so maximum value of r1 plus r2. So we need to see the combinations here. r1 r2, the product is 64. So like what are the possibilities? 1 into 64, first possibility 2, 32, 4, 16, 8 into 8. So these are 4 possibilities which you can see here. And if we see the r1 plus r2, so in out of these 4 cases, r1 plus r2 is maximum only with this case. When r1 is 1, r2 is 64. Yeah, 64 and 1. So that means r1 plus r2 is 64 plus 1, that means 65, and that is the answer. Okay. So that was it. So that is the maximum value of r1 plus r2. Okay. Okay, so let's move to the next question. Next question is again like heat transfer question. Okay, the last question was like of the topic, okay, or like of another topic, current electricity. But anyway, both the topics are like similar. Okay, at some aspect. Okay, so now see, let's see this question. And again, this is a good question, and like somewhat this question is like related to the first question. Okay, let's see here. Two identical plate sheet each behaves like a black body, are kept parallel to each other with small separation between them in vacuum. Thermal energy is generated at constant rate P in one of the sheets by passing electricity in it. Okay, so that we are providing the extra power to the battery through electricity. In steady state, temperature of the other sheet is found to be constant 300 Kelvin. Find the value of P in kilowatt. Okay, the thing is like in this one we have 2 sheets, right? Let's see the first sheet here. First sheet is, let's say, that's the sheet which is absorbing the power from outside. So it's taking heat from outside, and there's the another sheet placed, the second one. This is first one, this is second one. The thing is like this first sheet, okay, is absorbing power from the outside through electricity, and it can absorb the power from second also. If the second also has some temperature, 300 Kelvin, that is given constant. So first up now they see the first has a area and a surface area here. So it is absorbing heat from both the surfaces, left surface, right surface. So again like the area will be 2 times. Okay, and but the second one is releasing heat, okay, which is being absorbed. Okay, anyway, but it is releasing heat from one surface only. Okay, this heat which we will not consider because it is like going away into the surrounding. Here we will consider only like the heat which is released and as well as absorbed. So you can see here the first for first sheet 2 surface areas are considered. For the second only 1 surface area is considered. Okay, so now how to write the equation? So I'm writing the equation. First is taking the heat from source, from the electricity. So P is the heat, the power which is absorbed through electricity, plus it is absorbing heat from the second also. So sigma A T2, let's say its temperature is T, okay, it is given T2 and T1. So T2 to power 4 is equal to this heat which is absorbed now releasing, because it is a black body. So black body, whatever it absorbs, releases everything. So how much it will release from both the surfaces. So what will write? So sigma 2A will come. Okay, because both the surfaces are considered. T1 to power 4. So that is our first equation. First of all. Now let's move to the next case. The absorption of second. Okay. sorry, yes. Now the first one, yeah, this is it. Up, see here, the first will absorb, will release heat in this direction, in this direction. Similarly, second will release heat from this direction to this direction. But if you see these two sheets only, at steady state we are talking about now. So at steady state, the heat which is absorbed by one, this heat will be absorbed by two, and the second one, okay, which is okay. Now the second one. So first we consider the first, okay, in the first case the first sheet which is absorbing heat, okay, from outside and from the second plate, and releases heat. Okay, now second, now see the steady state. In steady state, the second one, which is at like T2 temperature, will release heat, right, in both the directions, here and here. Okay, but so the second one is releasing heat now. Okay, but the first one is absorbing heat only like on its surface, one surface only, right? The first, okay, so second plate is releasing heat from both the surfaces, but the first one, okay, which is absorbing the heat which is released by second one only on one surface. Okay, so this case, when the second is releasing heat now, okay, the second is releasing heat in both the directions from both the surfaces, but this time the first one is absorbing heat. Okay, it's not absorbing it from the outside. Okay, that is done. At steady state we are like considering here. So at steady state, this first will absorb heat, okay, from the second one only, like from this surface, on the right side surface. So this time we'll consider the only surface, one surface area of the first plate, and steady state we know the rate of heat will be same. So sigma A T1 to power 4 will be equal to sigma 2A T to the power 4, because the second one will release heat in both the directions from both the surfaces. Understood here? So that is the rate of heat exchange basically. So that is our second equation. Now if we substitute and find the value, so like in this one, P is equal to I'll put the value of sigma A T1 to power 4, which is sigma A T2 to power. So like it is coming as 2 sigma A T1 to power 4 minus sigma A T2 power 4. Now if we put the value this one from second equation, so it becomes 4 sigma A T2 power 4 minus sigma A. So it makes 3 sigma A T2 power 4, and that will give us the answer. Now power is equal to 3 into sigma is 17 by 3 into 10 to power minus 8 into area, this 10 to power 3 on 17 into 27 into temperature, which is 300 to power 4. Now we'll see, like everything will be cancelled here. I think 17 70 cancel, 3 10 to 00 is there, 00 10 to power 8, so that will also be cancelled. 3 to power 4 is 81, and 27 into 3 is 81, so it is also cancelled. So with what we are getting, 3 into 10 to power 3 watt. So the answer is to find the value of P in kilowatt. That means P is equal to 3. So that's it. I hope you understood. So thank you. Okay, so that was about this one. Okay, so if there's any confusion in this last part, so I'll just clear it again. See, the first and the second, two plates are there. Okay, first equation, I hope it is clear. The second equation is steady state. Okay, what it says that the temperature of the second sheet is constant. Okay, and if you know, like when the temperature of the sheet is constant, that means rate of absorption and rate of release both are same. in the form of radiations only. Okay, so that is there. So that means the temperature of second plate is constant. That means whatever it is absorbing, it is releasing. You getting my point here? So okay, how much it is absorbing? So it can absorb only from first. How much? Sigma. How much it will absorb? The amount the first one will release. How much the first one will release? So sigma 8 T1 to power 4. Understood here? This is the absorbed by second. Whatever it absorbs, it has to release. It can release the heat from both sides. You getting my point here? So sigma, so that's why I took 2a and T2 to the power 4. That's it. So this is absorbed rate and this is the released rate. Both has to be equal, then only the temperature remains same. Okay. So I hope it is clear now. So thank you.